In this video, we are going to talk about ordered fields, and ordered fields should be very familiar to you because the numbers, the real numbers, along with the regular addition and multiplication that you're used to since that you've used since first grade or kindergarten, are an example of an ordered field. On one hand, you have this big advantage because you are familiar with ordered fields and you've been working with them and all the properties of ordered fields as you went through algebra. However, it's easy to take those things for granted, and so what you may not realize or have not thought about is there are other systems, sets, and operations that may not follow the same algebraic properties you are used to. So for example, vectors, you can't even really take a multiplication for granted. There are two ways to multiply vectors, dot product and cross product, unlike real numbers. Or let's say another system, matrices. So you can't take the commutative law of multiplication for granted when you're doing matrices. So a lot of these properties that you have taken for granted with the real numbers, we're going to take a closer look, and we want to not take them for granted and prove that we can still do the things that you're expecting. So here is the first overview slide, and this is the second overview slide. We are going to start with the field axioms. So that is a set of real numbers with two operations, addition and multiplication, the same addition and multiplication you've been doing since kindergarten. We're going to, the field axioms give us properties about addition and multiplication on the real numbers. The first property we're going to talk about is closure. So addition and multiplication are both closed on the real numbers. So in other words, if you have x and y, that is both of them are real numbers. When you add them together, you get back a real number. And if x and y are real numbers, when you multiply them together, you get back a real number. In contrast, the natural numbers do not have additive inverses because you would need negative numbers. And also the integers is another example. They do not have multiplicative inverses. The next property we will talk about is commutativity. So addition and multiplication on the real numbers is commutative. So for example, if you take two real numbers and you add them together, you can switch the order of the two numbers and you still get the same sum. Similarly, for multiplication, if you multiply two real numbers, you can switch the order of the two real numbers and you should still get the same product. You can contrast this with the set of matrices under matrix multiplication. It is not commutative. In general, M1 times M2, matrix 1 times matrix 2 is not equal to matrix 2 times matrix 1. Both addition and multiplication of real numbers is associative. Both addition and multiplication have an identity element. The additive identity, also called 0, is a unique real number 0 such that x plus 0 is equal to x. The multiplicative identity, also called unity, is a unique real number called 1 such that 1 does not equal 0 and x times 1 is equal to x for all x in R, for all real numbers. And along with the identity, you then can get an inverse for both addition and multiplication. So the additive inverse, for each real number in R, there is a unique real number, we'll call it negative x, such that when you add them together, because it's an additive inverse, you get back your additive identity. The multiplicative inverse, so for each x in R with x not equal to 0, there's a unique number, which we designate 1 over x, such that x, the product of the inverse times x, is equal to the multiplicative identity. And our last axiom is the distributive law, which relates multiplication and addition together. So if you have x times a y plus z, and y plus z is done first because it's in parentheses, then you can distribute your x, so you have x times y plus x times z. So you distribute the multiplication over addition. Other examples of fields include the set of rational numbers and the set of complex numbers. Both of these sets along with the operations of normal addition and multiplication. The smallest field you can have has the additive identity and the multiplicative identity, 0 and 1, and you'll have to define 1 plus 1 equals 0. I will show that this new field satisfies the field axioms. Here is my field, and I'll start with the addition axioms. So first I'll show that addition is closed. So I've written out, there are only 2 elements in the field, so there are 4 ways of combining, or 4 combinations of the zeros and ones. 0, 0, 0, 1, 1, 0, and 1, 1. Remember, we don't know it's commutative yet, so I have to separate 0, 1 from 1, 0. So when I add 0 plus 0, I get 0. When I add 0 and 1, I get 1. When I add 1 and 0, I get 1, as you would expect. But when I add 1 and 1, I define that to be 0. And you can see here, I've defined everything so that the addition is still in the set 0, 1. So addition is closed. You can also see that addition is commutative. So when I've rearranged the 0 and 1, I still get the same answer. So 0 plus 1 is equal to 1 plus 0. Both of these, this side here on the left-hand side is equal to 1, and this side here on the right-hand side is equal to 1. To do associativity, I needed 3 elements. So I needed to have all possible combinations of 3 zeros and 1s. So what I did is I counted them off in binary. So this is with only 3 bits. So I have 0, 1, 2, 3, 4, 5, 6, and 7. So I have my case of 0 here and my case of 7 here. And from there, I have the other 6 as 1, 2, 3, 4, 5, and 6. So in other words, 6 had the 1, 1, 0. And then I just rearranged the parentheses, right? And this one I told you was 4. So it had the 1, 0, 0, which was this case here. I'll walk you through 2 of them for how I got this as being associative. So this one's kind of easy. I have the 1 plus 1 plus 1 is equal to 1 plus 1 plus 1. So when I do this part of the 1 plus 1 first, I get the 0, and I add it to 1, and I get 1. Here I get the 1 plus 1 here. I get the 0. I add it to the 1, and I get 1. This one's a little more interesting. I have the 1 plus 0 and the 1 plus 1 plus 0. So when I add the 1 plus 0 first, I get the 1, and then I add this one and I get 0. Whereas here I add the 1 plus 1 first and get 0, but I add it to this 0 and I still get 0. And you can verify all the other cases for associativity. 0 is the additive identity because when I add it to anything, such as 1, I get back what I started with. The additive inverse, 1 is its own additive inverse because when I add it to itself, I get the additive identity, and 0 is its own additive inverse because when I add it to itself, I get back the identity. To show multiplication is closed, I've written out all the possible combinations of 2 elements from the set, and I did the multiplication, and you can see that their product is always still in the 0, 1 set. To see that it's commutative, I see that 0 times 1 is equal to 1 times 0. Both are equal to 0. Here you can see multiplicative is associative, and because whenever there's a 0, everything's going to be equal to 0, so the only one that's kind of different is the 1, but then it's just equal to 1, so it's actually not that interesting. Multiplicative identity is equal to 1 because 1 times anything is equal to that anything. So when you multiply 1 times 0, you get back 0. When you multiply 1 times itself, you get 1. 1 is its own multiplicative inverse because when you multiply by itself, you get back the multiplicative identity, and 0 does not need a multiplicative inverse because when you talk about multiplicative inverses, you're talking about non-zero elements of the set. Okay, I used my same trick here with my binary to get my 8 cases for distributive law, and I'll just go over 2 of them, or 3 of them. So I'll do this one first. Actually, I'll do this one. Here is my 0, 0, 0 case. By the way, this is my 1, 1, 1 case. But I'm going to do this case, my 0, 1, 0 case. So I have 0, 1, 0. and by the distributive law, that should equal to 0 times 1 plus 0 times 0. Here, when I do the 1 plus 0, I get 1 times 0 is 0. Here I get 1 times 0 is 0 plus 0 times 0 is 0, which is 0. So this works. So I'll come down to this one because it's more interesting. This is my 1, 0, 1 case. In other words, I have 1, 0, 1, and that should equal to, by the distributive law, 1 times 0 plus 1 times 1. So this is 1. When I add these two together, I get 1, and 1 times 1 is 1. Here I have 0. My 1 times 1 is 1. So I have 1 is equal to 1. On this one, this is not my 1, 0, 1 case. This is my 1, 1, 0 case. In other words, my 1, 1, 0. By the distributive law, it's 1 times 1 plus 1 times 0. So here I have 1 times my 1 plus 0 is 1, and that's equal to 1. Here I have my 1 times 1 is equal to 1, plus my 1 times 0 should be 0, so that's also equal to 1. Now I have demonstrated this very small field satisfies all the field axioms. Our first example is to show the set of irrational numbers is not a field. The rational numbers, they do follow commutative and associative laws, but they are not closed. So for example, 3 minus the square root of 5 and 3 plus the square root of 5 are both irrational, but their sum and products are rational, so you cannot do the sum and products and stay within the irrational numbers, which means addition and multiplication of rational numbers is not closed. And this is an example of why you can't take every set along with addition and multiplication for granted that is going to give you a field. And if you're not in a field, not all the algebraic properties you're used to will apply. I moved that example here to give us more room. So next is the order axioms, and that is less than or greater than. The relation satisfies the following properties. First is the trichotomy law. So the idea is if you have two numbers, when you want to compare them, they're going to be one of these three relations. Either they're going to be equal, x is greater than y, or x is less than y. So three different relations you can have on two real numbers. Next is the transitive property, which you're familiar with. If nothing else, we talked about that in equivalence relations. So if you have three real numbers, if x is less than y and y is less than z, then x is less than z. And then also for all real x, y, and z, if you have x less than y, then if you add z to both sides of the equation, the inequality is preserved. And if you have x is less than y and z is greater than 0, and you multiply both sides of the equation by z, the inequality is preserved. These four properties are what allow you to order the set of real numbers. And any field that satisfies the ordered axioms is called an ordered field. That is, the set of real numbers is ordered because they follow the order axioms. Any field that satisfies the order axioms is an ordered field. So the set of real numbers is an ordered field. We have a theorem here for x, y, z, and r. We have a cancellation property, we have the zero multiplication, and a few other properties that you can take a look at, and we are going to do a couple of proofs. The first thing we want to prove is this cancellation property. Here, I moved my theorem over here to give me space. So this is the cancellation property. So if you have real numbers x plus z, and it's equal to y plus z, you can cancel out the z's and get x equals y. And the reason why you can do that, you want to use your field axioms here. And it's very much like what you used to do in algebra when you first learned algebra in, I don't know, 5th or 6th grade. What you would do is you would subtract z from both sides, and you'd be using the idea of an additive inverse. So here's our proof. We start with x plus z is equal to y plus z. As I mentioned, we're going to subtract z from both sides, and we're doing this, we're calling on the fact that every element, z, has an additive inverse. We're also calling on the fact that the addition is closed. So we're still doing this, we're still going to stay in the real numbers. Next, we want to group the z along with its additive inverse so we can then get the additive identity 0. So we're going to group them together, and we can do this because addition is associative. So we do the grouping on both sides of the equation. Then we use the fact that when you add z with its inverse, you're going to get the additive identity. And our last step is to remind ourselves that 0 is the additive identity, so we have x equals y. Again, this is almost like going back to 5th or 6th grade, where you used to have to justify all your little steps. I will say this next one would have been hard for a 5th or 6th grader, so we're going to prove that x times 0 is equal to 0. To do this problem, we're going to use the fact that 0 is the additive identity, that it's kind of special. So to this 0 here, you can add another 0, and it'll still be equal. And then you can use the distributive law to distribute. And now I'm going to look at this original equation again, x0 equals 0. And I'm going to use again the fact that 0 is special, it's an additive identity, and I'm going to say that this x0 here is equal to x0 plus 0. Combining these two lines, since they're both equal to 0, I'm going to set these two lines equal to each other. So I have my x0 plus x0 is equal to x0 plus 0. And finally now I can use cancellation, part A of my theorem, to cancel out the x0, and I get x0 is equal to 0. Our next proof is that negative 0 is equal to 0. And we're going to consider 0 is equal to 0, which is certainly true. Then we're going to add another 0 to this 0 on the left-hand side. So we're going to have 0 plus 0 equals 0. But by A5, which is our additive inverse, negative 0 is the unique additive inverse. So in other words, if we add something to a real number x, and get back x, then this something must be the additive inverse. So I wrote this out so you could see it. I have my 0 plus 0 is equal to 0. And this 0 here, when I have two things added together, equals the additive identity. Well, that must mean, because there's only two things, that must mean the second thing is the additive inverse of the first thing. And the additive inverse is unique, which must mean that minus 0 is equal to 0. Or another way of looking at this is we have 0 plus 0 is equal to 0. We also know 0 plus its additive inverse is equal to 0. So these two things are equal, and then by cancellation, we have 0 equals negative 0. Next, we want to prove that negative 1 times x is our additive inverse of x. Since we're looking at additive inverses, what we will do is we will start on the left-hand side, the negative 1 times x, we will add x. Since multiplication is commutative, we can switch the order of the negative 1 and the x, and then to this x here, we can multiply by the multiplicative identity, and that will allow us to use the distribution law to group the 1 and the negative 1 together, and when we add them, we get 0. By our last theorem, x times 0 is equal to 0. What we have shown is this negative 1 times x added to x gives us 0. And since the additive inverse is unique, that must mean that this negative 1 times x is equal to the additive inverse. The next proof we have is if x times y is equal to 0, that means either x is equal to 0 or y is equal to 0. And I really like this proof because it demonstrates the use of the or can suggest cases. In particular, if we start with let x times y equal 0, then we can assume the two cases are either x equals 0 or x does not equal to 0. So these are our two cases, and it's really nice because if x is equal to 0, we're done. And if x is not equal to 0, we actually need to show that y is equal to 0 now. But it's nice because now we have the extra information that x does not equal to 0. And looking at my original equation, I want to isolate my y. X does not equal to 0, so that means I can multiply both sides of the equation by x inverse, or in other words, dividing both sides the equation by x. But here I have multiplied this side of the equation by x to the minus 1, the multiplicative inverse, and then I have this side of the equation, the 0, multiplied by my multiplicative inverse. By commutativity of multiplication, I can rearrange these elements, and then I get x times x to the minus 1, or inverse. So this part here is equal to 1 times y. That will just give me y, because 1's the multiplicative identity. And here, 0 times anything by my theorem is equal to 0. So now I have proven that y is equal to 0. And again, I just wanted to mention one of the things I like about this proof. If you have to prove one of two things are equal, in this case we're proving either x is equal to 0 or y is equal to 0, you can break this up into cases where one of the cases you can just assume is true. And then the other case would have to be that your x is equal to 0 is not true. But the nice thing is when you come to this case, then you're done with your whole proof, because you only have to prove an or. And then then you are only left with proving the case where that your first case is not true. But in this case, case 2, when you're proving y equals 0, you also get the additional information now that x is not equal to 0. Part F is fairly straightforward, but I have the proof here along with the justifications. And part G is also fairly straightforward. It does use part F, the theorem that we just proved. Our next topic is to show that the rational numbers is also an ordered field. And just to remind you, the set of rational numbers are the numbers that can be expressed as m divided by n, where m and n are integers and n is not equal to 0. Since the rational numbers are a subset of real numbers, the commutative, associative, and also the distributive laws and the order axioms are automatically satisfied. So I checked them off here, off of the field axioms. So addition, associativity of addition and multiplication, and the distributive law. Again, those properties all carry over because rational numbers are a subset of the real numbers, and we've already determined that the real numbers is an ordered field. So the things we need to show is that addition is closed, the additive identity and additive inverse are part of the rational numbers, multiplication is closed, and the multiplicative identity and multiplicative inverse are also part of the rational numbers. So first are the identities. So the additive identity is 0, and that is also a rational number. Just take m is equal to 0, n is equal to anything, and you'll see that the 0 can be written as a rational number. Also for the multiplicative identity, 1 is also a rational number. Just take m is equal to n, and you'll get 1 as a rational number. So then we'll look at additive inverses. So if you have a rational number, m over n, then negative m over n is also a rational number, and that's exactly what you need to get the additive identity. When we look at multiplicative inverse, if you have m over n, then n over m is also a rational number, and when you multiply them together, you get the multiplicative identity. So now all we need to show is that addition and multiplication are closed. So first we'll look at addition. If I add m1 over n1 plus m2 over n2, I get another rational number. So addition is closed. If I do the multiplication, no, that's over here, multiplication. So if I multiply m1 over n1 times m2 over n2, you can see I still have a rational number. So now these are taken care of, and we have satisfied all the field axioms and have shown that the set of rational numbers is an ordered field. Next, we will see that f1, the set of rational functions, that is, f1 is the set of all quotients of polynomials. They have this form. The f1 is a field, and it's also an ordered field. And the order is defined by this equation here. So if we have two polynomials, p over q, and another polynomial, f over g, then pq is greater than fg if we put them over the common denominator, qg, and then cross multiply so that pg minus fq over our common denominator is greater than 0. I will not go through verifying all the field axioms for F1, but I will show you how this ordering works. And one thing to note before we do these examples is that the quotient of these polynomials is positive if and only if the largest exponent on the top, the coefficient of the largest exponent on the top have the same sign. So here we have 3x squared and 7x to the fifth, they are the same sign, so the quotient is greater than 0. However, here we have the 4x to the fifth and the minus 7x to the third. Their signs are different, so the quotient is less than 0. The first example I have is which is larger, x squared or 3 over x? To evaluate this, we're going to use our formula here. We're going to do our common denominator, so over x, and then we're going to cross multiply. So here we have x times x squared is x cubed, 3 times 1 is minus 3. So we're going to see if this is true because this is greater than 0 because x cubed and x have the same sign, which means x squared is larger. Our next example, which is larger, x over x plus 2 or x over x plus 1. Again, using our common denominator here, we multiply these together and then we cross multiply, we get x squared plus x, and then cross multiplying here we get minus x squared minus 2x. And now we look at this, so these two cancel, but our largest exponent on top is negative and our largest exponent on bottom is positive, which means that the quotient is less than 0. So now that means that our second quotient is x over x plus 1 is larger. The next theorem is to let x and y be real numbers such that x is less than or equal to y plus epsilon for every epsilon greater than 0. Then that would mean that x is less than or equal to y. And we're going to do this proof using the contrapositive. First, I want to get the contrapositive, so I wrote this as an implication that for every epsilon greater than 0, x is less than or equal to y plus epsilon implies that x is less than or equal to y. So the contrapositive is the negative of the consequence, so x is greater than y, implies the negative of the hypothesis. So we negate the for all with the there exists such that x is greater than or equal to y. So this is the contrapositive I'm going to prove. Since what I'm trying to prove is that there exists an epsilon, I just need to find an epsilon that satisfies this condition. So I rewrote the condition, x is greater than y plus epsilon. So I have epsilon is less than x minus y. So any epsilon less than x minus y. So I'm going to choose epsilon equals y, x minus y over 2. And often, when you have epsilon is equal to some condition here, you often just divide it by 2. And that's a convenient way of doing this. But of course, any epsilon that satisfies this condition would have been okay. And in the next slide, I choose a different epsilon. But this is the one I'm going to use for this example. Then what I get is y plus epsilon is then equal to y plus, substituting my x minus y over 2 over here. I do the algebra and I get 1/2 y plus 1/2 x. So I kind of rewrote that over here. My y plus epsilon is equal to 1/2 y plus 1/2 x. But since x is greater than y, if I substitute x here, then I'm going to get y plus epsilon is less than, because now this is going to be greater than 1/2 x plus 1/2 x, which is equal to x. And I get exactly what I'm looking for. If I let epsilon equal to x minus y over 2, then I'll have x is greater than y plus epsilon. During this proof, I had told you I had chosen this epsilon equals x minus y over 2. And often when I see proofs, people often do the division by 2. But I also wanted to show you that isn't the only choice you could have. So on the next slide, I'll show you when I choose epsilon is equal to x minus y minus 1. So as I had mentioned, if I'm doing this, trying to prove this contrapositive, and I'm considering x is greater than y plus epsilon, that is that epsilon is less than x minus y, then I really could have chosen epsilon equal to x minus y minus 1. And then I would have gotten y plus epsilon is equal to x minus 1. So I could have chosen y plus epsilon. Oh, y plus epsilon is less than x. So I could have said, here's my epsilon. So there exists an epsilon such that x is greater than y plus epsilon, which is exactly what I wanted to show. So this would have been another good epsilon. Any epsilon that satisfies this condition, you can put into a proof. Here is the last proof we just did. The next thing we want to talk about is absolute value. So it's the same as what you know from algebra. The absolute value of x is equal to x if x is greater than or equal to 0, and negative x is if x is less than 0. So we have this theorem, let x and y be real numbers and a is greater than or equal to 0. Then the absolute value of x is greater than or equal to 0. It's less than a if and only if x is between minus a and a. We have this multiplication, which is left as an exercise, and we have the triangle inequality. And one thing I'm going to tell you about the triangle inequality, you've probably seen this before in algebra and maybe calculus, and this is definitely something you want to remember. You'll be using it sort of a lot in a future chapter, so you might as well kind of remember what it is. And it's called the triangle inequality because we can think of the real numbers as points on a line. Then AB represents a distance from A to B, and then you have thus the distance from A to B is less than or equal to the sum of the distance from AC and CB. So these two, the hypotenuse is going to be less than or equal to the sum of the two sides of a triangle. We've gone through all the main points, and so now we're ready for some review problems. Here's a set of review problems for you to try. Pause the video, give them a try, and on the next slides I'll have solutions for you. This is the solutions for the first problem. These are the proofs for the next two problems, and I do have a comment on this one in this inductive proof. To go from this left-hand side to this right-hand side, I grouped these together as one single number because you can add these real numbers. So I have one group of real numbers and another group of real numbers. So I use the inequality to go from this side to this side of the equation. To go from here to the next line, I use the inductive hypothesis. And this is the solution to the last problem with the solution here on the bottom. That is it for this video. Thank you for watching.